Hope everybody's doing well. We're going to go ahead and get things rolling. If you haven't looked at what I put on Google Classroom yet this morning, it is worth a look. The most important thing is, and we'll get more information on this soon if your teachers haven't already started talking to you about it, is that the end of, like, we need to have your work turned into us by next Friday. That's basically what it is. So that we can get our final grades finished and that type of thing. In lieu of exams, we have to find something else for you guys to do, and we'll learn more about that as it gets here. But for right now, just know, test this Friday on Unit 6. That means tomorrow you guys will have a little more time to work on the Unit 6 review and the Unit 6 vocab. In fact, Unit 6 review is something we should probably talk about, so maybe we'll do that in here as well. We'll go over that too. But anyway, test this Friday. We'll do a little bit of work next week just so you guys have seen a little bit about acids and bases. And yeah, we'll just see what we can get through. And then after that, it is a brave new world out there. I'm not really sure what comes next. So just know that, be aware of it. Everything's going to be great. All right, so let's switch to desktop. Go here. Hope everybody's doing well this morning. Hope you're looking forward to the summer, such as it is, just like I am. And it'll be here before we know it. All right, so this was the first thing that I wanted to talk about, which is a quiz that you guys are actually taking today. So if you haven't taken it, try and do it. Try and do it on your own. But anyway, it's a pretty easy quiz. This quiz, the hardest part for you guys is going to be problems 6 through 10, but the rest of it basically just comes straight from your equation sheet. I've got my equation sheet right here. Super easy. All right, so let's see. Number 1, what does the variable m stand for? It does not stand for moles, which is something I bet a lot of students would try and do. M, lowercase m, just stands for mass. Okay, so I don't want you to be confused and think, oh, well, I thought m stood for moles. No, lowercase m was already taken a long time ago by Isaac Newton, before moles were really something we were talking about in chemistry. Newton had it in physics as a lowercase m, and so that's what we use. Capital M stands for molar mass. Okay, that stands for the molar mass. So, for instance, 16 grams per mole for oxygen. Okay, so that's molar mass. Variable R, this is just the gas constant. What specifically does the reference table call it? Yep, they just call it gas constant. So there you go. That's what I'm going to call it. Real difficult stuff. And then the next part, slightly trickier, but still not that bad. It says, what is the value of R given the following unit? So remember, guys, R, you have 3 different values for on your reference table. And if you go to college, and you're taking a college level class, same thing. You'll be given the R constant. But there are different situations, and in different situations, you have to use different ones. And it's usually based on pressure. So we can see that the unit of pressure in number 4 is atmospheres. So when you're dealing with atmospheres, we're going to go ahead and make it this value, 0.0821 liters times atmospheres over moles times Kelvin. Okay, so that's the number we want. But in number 5, it says, what is that? That looks like an 8. Let's make that a 0, because that's what I was going for. There we go. Number 5, what is the value of R given these units? So now we have kilopascals, kPAs. So when you have that, we're going to use this value, 8.314. Okay, so there you go. Really not that bad. I'm literally looking at the equation sheet, I'm writing it down. All right, now for number 6 through 10, these are the ones that I'll admit, these are a little bit trickier, especially since the main question I'm getting from students is, can you help me with the algebra? Like, how do I solve for blah if I'm given this and this and this and this? Okay, so I know that can be kind of tricky. Algebra is something I don't really have time to teach y'all. Like, that's something that you want to know that. You want to know that by the time you get to chemistry. But I'll do a little bit. I can do a little bit. So D equals M over V is used for density problems. Manipulate the equation to solve for mass. So, all right, we've got D equals M over V. We're trying to get mass by itself. So I need to get rid of volume. If I'm trying to get mass by itself, I need to get rid of volume. So if I multiply by V, that's the opposite, all right? I'm dividing by V. So if I multiply by V, that will help me cancel it. And whatever I do to one side, I have to do to the other side as well, which is why this one ends up being M equals V times D, or D times V. It's the same thing. All right, so that's what we end up getting. Let's look at number 7. Pivinert, or PV equals nRT, is the ideal gas law. Manipulate the equation to solve for temperature. All right, so same kind of thing. So I'm going to go ahead and write it. PV equals N times R times T. And they are multiplication. Okay, there's a dot there, there's a dot there. N times R times T, P times V. So they're all there. It's just that usually that's not written. So if we're trying to get temperature by itself, that means we need to get rid of N and R. So once again, instead of multiplying, okay, times N and R, we're going to divide by N, and that cancels N. And we're going to divide by R, and that cancels R. So by dividing by N and R, okay, we get PV over NR equals T. And so T is left by itself over on that right side. So anyway, this is what we end up getting. But again, it's the same thing. You want to get rid of something, do the opposite. So if you're multiplying, divide. If you're dividing, multiply. And again, whatever you do to one side, you have to do to the other side. All right. Now we're going to use the ideal gas law again for our next problem. Because the next problem says rearrange the ideal gas law to solve for volume. So this one's actually easier. As you can see, volume only has one other term with it over on the left side. It's pressure. So if I'm multiplying by pressure, dividing by pressure is going to help me get rid of it. And once again, whatever I do to one side, you have to do to the other side. So V equals, all right, we can see it there now, V equals N times R times T all over capital P for pressure. All right, let's look at number 9. Same thing. Says Q equals mc delta T is the equation to solve specific heat problems. Rewrite the equation for Cp, and Cp here stands for specific heat. So if we're looking for Cp, and this one can be a little bit tricky because a lot of students see C and P and they're like, oh, are we doing, or is this C times P? No, the P is part of it, okay? P is part of it, so it's part of the variable. It's kind of like how earlier in the unit we would say Ti meant initial temperature, or we might say Tf meant final temperature. In physics, if you guys ever take physics, you'll find out there are lots of forces. We would have force of, force applied. We would have force of gravity. We would have force of tension. We would have something called the normal force. We would have something called force of static friction. And so as you can see, you add all these subscripts just so we know specifically what you're talking about. So don't get confused by subscripts. So in this then, I'm going to write it out. We have Q equals M. I'm even going to put some dots in there to help you guys. Times Cp times delta T. Delta T is one big thing. It doesn't really matter so much for this problem, but it really means T final minus T initial. But we don't care about that here. We really don't care. In fact, that'll make it more confusing because all we're trying to do is rewrite the equation to solve for Cp. And we can do that. So again, if I'm multiplying by M on the right side and I want to get rid of it, dividing by M on the right side, it's going to make it cancel. It's going to make it go away. And again, if I divide by M over there, I got to divide by M over here as well. All right, here, let me rewrite what we got down below. So now I have Q over M equals Cp, oops, that's not where I want to put that, times delta T. So once again, I'm multiplying by delta T, so if I want to get rid of it, I will divide by delta T, okay, and that's going to make it go away. But again, whatever you do to one side, you have to do to the other side, and so delta T ends up going right there. So what I end up getting for number 9 then is Cp is equal to, okay, Q, whoa, that's a really bad Q. Let's try that again. Q over M times delta T. There you go. There you go. Please load. Don't be like that, internet. There we go. That's some real slow internet today. I think it's because everyone in America is using the internet right now. All right, number 10. M1V1 equals M2V2. This is one of our gas laws. It's not the ideal gas law, but it is one of the gas laws, so it's going to be useful. So M1V1 equals M2V2. It's called a molarity equation. What's important is we're doing math here. In fact, I need to put a star next to that. Used to, I would teach Unit 7 before Unit 6, and you guys would know more about what molarity actually means. So don't sweat this one that much. But the thing is, you can still do the math. If I have M1V1 equals M2V2, you can solve for V2. You're using the same things that you've been using before. It's the same thing. So if I'm looking for V2, I need to get rid of M2. And so if they're written that way, that means they're probably being multiplied by one another. So if I want to get rid of M2, I'll just divide. Whatever you do to one side, you do the other side. So we end up getting that. And so boom, here we go. V2 is equal to M1 V1 over M2. Piece of cake. Determine which equation to use given the following variables. And there's no need to manipulate the equation here. So literally, you've got to think, I've taught you guys 5 steps to doing math problems. So here we go. Here's step number 1. Here's what you know. Here's step number 2. Here's what you don't know. Step number 3 is finding what equation is going to work. So this is the first 3 steps. And 1 and 2 have already been done for you. So literally, you take your equation sheet. Okay, this is really easy. Take your equation sheet, go over here where they have the formulas, and you're trying to have a formula that has all the letters. So if I look at the first row right here, I'm looking at the first row. I'm like, all right, I've got a P, a V, R, T, and N. And then I look at my equation sheet, and I say, well, oh, here it is. PV equals nRT. That has everything that we know and what we're looking for, which in this case is N, number of moles. Next one, same thing. We say, all right, well, here's the equation we have. We have M and HF. HF. There's literally only one equation that has HF in. It looks like this. Q equals M times HF. So there you go. Still not confusing. Next one is Dalton's law. Spoilers. Is we have P1, P2, P3. And we have P total is what we're looking for. So this is just Dalton's law. You guys took notes on that. Not equals. If you took notes on that, this should be familiar. It's one of the easiest ones. Okay. Next one. We have mass and volume. And if it helps you, you can rewrite it and say, well, this is M. And this is V. And we're looking for D. Oh, it's that one. D equals M over V. Which is an equation you probably learned in middle school, honestly. You probably learned D equals M over V in middle school. Next one, maybe we'll do the same thing. We'll say, well, heat energy. Heat energy is usually measured in Q. Why is it a Q? Because it stands for quantity of heat energy. Then we have mass. That's going to be a lowercase m. And we have temperature. Okay, which temperature kind of annoys me. It's listed as temperature here. I would rather it said change in temperature. That's represented with a delta. Delta means change in. Here, I'll even write it. It means change in. But yeah, whatever, same thing. And we're looking for specific heat. And specific heat is CP. And you're saying, well, Mr. Aaron, how do you know that? Again, on the equation section, it tells you CP is specific heat. So it tells you what all this stuff is. And so I know the only equation that's going to work here is this one. Q equals M times CP times delta T. It's the only equation that's going to work. And honestly, if you just gave me this with just a T, I'd probably be happy. That'd be okay. But really, there is a delta that goes there. All right, I'll go ahead and say questions 16 through 20, Mr. Perugini wrote, and it's because in physics, which he teaches physics here at Inca, but I taught physics before, but in physics, you get these questions a lot. It's not as common, it's not as common in chemistry, but it's still kind of handy. I'll go ahead and tell you, 18 and 20, not super important for us. That's not something we've actually talked about yet. That's stuff that's going to be in Unit 7. And so I know you're saying, well, Mr. Aaron, you didn't give us Unit 7. I know that. We rearranged the units this semester, and we were going to make lots of changes, and then stuff happened. And so it's going to been a little more difficult. But anyway, we'll talk about those when we get to them. Number 16, if you double the mass of an object, what happens to volume? And if you guys look at your equation sheet, you will see there is only one equation that has mass and volume in it. That's this one right here. D equals M over V. Now, does it say anything about density? I can hear you through the comments section, even though nobody has said anything this morning. Is anybody even here? It'd be nice if people were actually here. 4 people? Good gracious. I can hardly contain myself. Thank you to the 4 people that are here. But you guys are probably saying, if they don't say anything about density, we're going to say that stays constant. So just assume this is going to be constant. That means it's not going to change. So in this problem then, if they say you double the mass, what do we need to do to volume so that density stays constant? Because the thing is, if I stopped right here and just said, okay, I'm doing 2 times mass, okay, then you're going to have 2 times the density too. Unless you also do 2 times the volume on the bottom. So if you double the volume, okay, if you double the volume, you're also, doubling the mass, and that means density stays constant. So the ratio stays the same. Another way to think about it is this, guys. If I have 1 liter of water, that's the volume, by the way, it has a certain amount of mass associated with it. If I have 2 liters of water, you'd expect it to be twice the mass. Don't overthink it, okay? Don't overthink it. So number 17. If you double the mass of an object, okay, what happens to density? So now they're not saying anything about volume. Now, this one I'll say is kind of a trap. In fact, I'm not real pleased with this question, number 17. I'm still going to write D equals M over V. And so if you answer it the way that you're supposed to, like we just did, and you say, oh, well, I'm doubling the mass, so 2 times M, okay? Does it say anything about volume? No. So we'll assume volume stays constant somehow, okay? Then you have to say, oh, well, if you double the mass, whatever you do to one side, you would then have to do to the other side. So it'd be 2 times the density. So here's the thing. If you said for this and said, oh, you double the density, good for you. Okay, that's fine. But in reality, density is something that stays constant. Okay, water, now obviously ice is different, but liquid water, even if you have twice as much water, still the same density. You have 4 times as much water, still the same density. So density is actually something that stays constant. So I would accept either of these answers. You could either say it doubles, because that's using the same method we used on 16, or you can just say it stays constant. Number 18, if the volume of a substance doubles, what happens to molarity? I'll give you the answer if you want me to. Basically, molarity is something you guys don't know yet. Sometimes it's represented with a capital M. So I guess if you really wanted to, up here where we said molar mass, you could say molarity there, but I'd say molar mass. So molarity is equal to the number of moles per liter, okay, in a solution. So if you're making Kool-Aid and you dissolve a certain amount of sugar to make Kool-Aid, that'll give you an idea of the molarity of sugar in Kool-Aid. If you have twice as much, you're doubling the molarity. So molarity is another word for concentration, basically, but this is what it's equal to, moles per liter. So what it's saying in number 18 is it says if the volume of a substance doubles, okay, volume is represented by liters, y'all. So if you're saying, well, there's no V in there, but remember, volume is measured in liters, okay? So if you double your volume, then actually what you're doing, because mole stays the same, is it's like you're doing 1/2 the molarity. Now that was kind of tricky. That's a really big brain problem, but I really don't want to focus on it too much. If you'd like to look at it later and see what I did, you can, but otherwise we got to keep going. Number 19. If temperature remains constant, what happens to volume as pressure increases? Now, I think that you could try and use combined gas law here, but it would get really, really messy really quick. What I'm going to use for number 19 is just this one. PV equals nRT. Ideal gas law is a little bit easier, excuse me. So if temperature stays constant, okay, so that's going to be constant. R is literally called the gas constant, okay, so we'll put a C there. And N, number of moles, they don't say anything about the number of moles, so we'll assume that stays constant as well. So that means this whole right side, we need to keep it constant. We need to keep it constant. All right. So if pressure goes up, what would have to happen to volume in order to keep the two sides of the equation the same? So if pressure goes up, what would happen to volume? Well, it's going to decrease. Because if pressure goes up and volume goes up, then when you multiply the two, then you would expect this side of the equation up here to go up as well. But we don't want that. We're trying to keep that side constant. So it's going to have to decrease. Last problem is 11. Don't worry about it. We'll learn about it next week. All right, great. That was fun. Any questions so far before we move on to the next thing? We can do heat math. I think I actually want to go over the review first. But are there any questions before we keep going? Any questions? Any questions at all? Nobody's saying anything. Nobody's typing anything. I know there's a little bit of a delay, but come on. If you have questions, now would be the time to ask them. How many people we got? Did I lose anybody? No, we still got 4 people. When do you think vocab is going to be due and test is going to happen? So vocab is going to be due Friday. Test is going to happen Friday. Unit 6 review due Friday. So tomorrow test, you're going to have time to work on the Unit 6 review, and you'll have time to work on vocab, and then we'll have our test on Friday. Any other questions from the comments? Said drink a little water. I needed an excuse to drink some water. That's really all. That's all that's happening. Okay, well, if you do, let me know. Let's take a look at the review. Okay, understand the relationship between pressure, temperature, volume, and phase. Fill in the blanks in the diagram below using the words provided. So they're giving us some words. You have to put everything where it belongs. We took notes on this at the very beginning of this unit, so it's appropriate that it's showing up now. But at the very beginning of the unit, I told you guys you need to know where everything goes, whether you're cooling down going one way or you're warming up going the other way. You have to know. You just have to know. In the Unit 6 review, hopefully, we'll get to them then. And I can go back, like I can answer some questions on this, the heat gas math practice. So if you do have questions on that, Emily, write them down. And when I get done with the review, I'll answer ones that you need. All right, so here we go. Let's put some stuff down. Let's start by, I don't know, let's start by warming up. All right. So obviously first we start with a solid, okay? Not really confusing there. We're going to start with a solid down here at the bottom. And then we get to this line. Now, we're going from a solid to a liquid. Okay, now that phase is called melting. Okay, it's called melting. Now, I have told you, and this will help you with college chemistry, this is also called fusion, because it is. That's my only answer. So if you're saying, you know, oh, I don't know, why is it called fusion? I don't know. My wife asked her. She's been teaching chemistry longer than I have. She doesn't know. All right. Next, we're going from C to E. So we start with liquid. We're becoming a gas. So the phase change of going liquid to gas, you might be saying, oh, it's evaporation. Wait, that's not an option. Oh, it's boiling. Wait, that's not an option. That's because this is vaporization. Vaporization includes both boiling and evaporation. So it could be either of them. Okay, there we go. Now we're going the other way. All right, here, let's get caught up. Solid, liquid, gas. We got, wow, melting. Wow, someone did not scramble these very well. The next one's probably condensation. Yes, it is. So if I'm going from a gas to a liquid, okay, you're going with, like, I don't know, water vapor in the air, and you're becoming liquid water droplets. So if you're going from gas to liquid, that's going to be condensation. Okay, that's going to be condensation. Next, if we're going from a liquid to a solid, which is represented by B, if you're going from a liquid to solid, that's going to be freezing. Not really confusing. And then, okay, we have these other boxes. They're a little more extreme. If you're going from, like I'll just show you, if you're going from a gas to a solid, which is what we're showing on this line right here, gas to solid. That's called deposition. Good example of that is frost. We had frost a couple days ago because it's May. Why wouldn't we have frost? And the other one is going from a solid to a gas. And so if we're going from solid to gas, that is called sublimation. Good example of that is dry ice, sublimation. Okay, so describe, now this is the question that several people had. Describe what is happening with the temperature, T, and energy, E, during the plateaus, okay? Whether you're moving up or down. So a plateau in geography, a plateau in geography terms is where you have like a flat hill that looks kind of like that, okay? In the Southwest, sometimes they call them a mesa, but it's also just called a plateau. It's a raised, flat place. So we have two plateaus, okay, on this. We have B and we have D. The plateaus are our phase changes. Okay, condensation and vaporization occur on D. Freezing and melting occur on B. So these are our phase changes. So there are only two plateaus. And so I'm asking you to tell me what happens with temperature and what happens with energy during these plateaus, okay, whether you're moving up or you're moving down. So in the first plateau, well, in either of them, temperature is staying constant. Temperature is going to be constant. Because as you guys can see, temperature is on this axis over here, okay? That's on the y-axis. And so it stays flat. It's not increasing or decreasing. So temperature is going to be constant. But for energy, okay, when you warm up, okay, when you're warming up, energy is increasing. Obviously, you know, if you need to melt ice, you have to put energy into it. So energy is going to be increasing. If you're cooling down, then your energy is decreasing. And that's really all I have to say about that. So even though, and the best example I can give you is your boiling water. When you're boiling water, you may want it to boil instantly, but that's not what happens. But while you're still warming it up, the temperature's staying constant. In fact, when you get to that point right before it's about to boil, you'll hear like a popping sound at the bottom of the stove. It sounds like it's creaking, you know, and just it's almost boiling. It's because you're adding energy in. You're trying to break the bonds between one liquid water molecule and another liquid water molecule. You're trying to break those bonds apart so it can finally become a gas. But it's because of the energy. All right, let's get moving. Matching. That's all I got to say about that. Matching. Wow. Sorry, I want to check on something real quick. All right, sorry. Got a nephew that's sick and I'm concerned about. Heat, temperature. All right, heat is going to be transfer of energy between molecules. There you go, G. Done. Temperature. Okay, temperature is a measure of the average kinetic energy in a substance, B. So when you guys hear about temperature, if something has a very high temperature, it just means the molecules are moving a lot. They're bouncing back and forth, back and forth, back and forth, back and forth. Okay. Next one, law of conservation of energy. Energy is not lost or gained. It only changes form. It goes from one type to another. Specific heat capacity. Okay. This is the energy required to raise 1 gram of a substance by 1 degree Celsius. Okay. In fact, that's why the units for specific heat are always joules per gram degree Celsius. It's how much energy in joules needed for 1 gram and to raise it by 1 degree Celsius. Heat of fusion. Remember, fusion is another word for melting. We're talking about melting. We're talking about going from a solid to a liquid. Okay, and so the answer here is going to be E. There you go. Next one, vaporization. We know vaporization is going from a liquid to a gas. It's going to be F. And then by process of elimination, C is going to be enthalpy, which is a word that you learn more about in college chemistry or AP chemistry. We talk about enthalpy a lot. All right, let's move on. Oh boy, a phase diagram. I love these. Good thing it's such a high-res image. All right, answer the following questions using the phase diagram for CO2 shown above. Number 1, what two factors determine phase of matter of a substance? Well, I'm going to go out on a limb and say it's probably going to be pressure and temperature based on the graph. Okay, so here is going to be pressure and temperature. Vapor pressure depends on what two factors? So vapor pressure is something that I guess I could tell you a little bit more about very quickly. Vapor pressure is where, right now in my water bottle, okay, it's sealed, all right? My water bottle is sealed, but as you can see, there's a little bit of air on the top. Here's my question for you. Is that water evaporating? I mean, look, we got a surface, we got a water level, so at the top part of this water level, is that water evaporating? And the answer is yes, to a point. At a certain point, because it goes from liquid water into water vapor. At a certain point, that little bit of air, okay, that's on the top of my water bottle right now here, I'll make it a little bit more air. Give me a second. That little bit of air, it's going to evaporate, evaporate, evaporate until that air has all of the water vapor that it can hold. That is called vapor pressure, because at a certain pressure, no more water molecules are going to have any room. Now, if I increase the pressure, I don't know, maybe I screw on the lid a little bit tighter, maybe I squeeze it, that's not going to work. It's a Nalgene, it's hard. But if I squeeze it, if I add more pressure, that means the vapor pressure is going to be a little bit lower because it's pushing that back into the liquid state. But at this point, you're going to see the water vapor is going to be increasing, and that's vapor pressure. So if I drink a little more water, vapor pressure is still going to be the same. It's going to keep adding water vapor molecules until that pressure is reached. Excuse me, I drank a lot of water just then. But if I drink more water, that just means there's more space for it, but it still is the same pressure. Now that that's clear as mud, yeah, what two factors? Well, depends on, that's not from the diagram above. Nah, I'm not gonna, you know what? I've already confused you guys enough. Let's not focus on number 2. Here you go. Omit. Because we got to keep moving. I've already confused you enough on that. Number 3, indicate on the diagram above the location of the critical point, the triple point. This right here is the triple point. Because triple point, as we know, that's where it's going to be a liquid, a gas, and a solid all at the same time. And the critical point is represented right here. Okay, there's the critical point. So critical point is represented by a C, triple point is represented by an X. Remember, at critical point, that's where the line becomes blurred between liquid and gas, and you actually can't really tell the difference between the two. Number 4, a sample of CO2 at 0 degrees Celsius is put in a pressurizing tank. The pressure in the tank is increased from 3 to 7 atmospheres. What phase change occurs? All right, well, let's see. So here's 0 degrees Celsius. Okay, there's 0 degrees Celsius. In fact, I'm going to go and give myself a dotted line because I'm going to need it here in a second. And it says the pressure is increased from 3 atmospheres. Let's go ahead and say 3 atmospheres is like right there. And let's say 7 atmospheres is like right there. And so if I start here and I end here, okay, what do we call that? All right, what phase change occurs? Well, we're going from vapor, which is a gas, into liquid. All right, we're going from gas to liquid. So if we're going gas to liquid, this is going to be condensation. Okay, number 5. It says, what is the approximate, so we're just guessing here, we're trying to get it as close as we can. What is the approximate melting point temperature of CO2 at 6 atmospheres of pressure? So, I don't know, 6 atmospheres, maybe like right there, let's say. And we're looking for the melting point temperature. So I'm going to just carry that over. Melting point is when you go from a solid into a liquid. And so it's going to be somewhere on that line right there at 6 atmospheres. And so that green dot I just drew, that's going to be it. So I can read this right here and see that says negative 56. This is going to be a little bit higher than that. So I don't know. Let's just say negative 55. Ooh. Or negative 50. We're just kind of guessing here. Okay, we're just trying to guess. It's not a very high quality graph. Number 6, dry ice as CO2 in the solid phase is stored in a colder than normal freezer temperature. So it's most freezers are at like 30, I don't know, 30 degrees, I think, Celsius, or sorry, 30 degrees Fahrenheit. But it's stored colder than that. When removed from the deep freezer, the carbon dioxide sublimates. Hopefully you guys remember sublimates is where it goes from a solid into a gas, forming a gas that's denser. Explain the reason for all of this. Well, based on the graph, we know that in order to stay solid under 1 atmosphere, and the reason 1 atmosphere is important is that 1 atmosphere is standard pressure, but it has to be negative 78 degrees Celsius. Okay, it has to be a lot colder. And so my answer for this would just be, well, CO2 freezes at negative 78 degrees Celsius compared to 0 degrees Celsius for water. There you go. That's good enough. That is good enough. All right, let's take a look at some heat problems. And guys, if I'm going too fast or you need me to re-explain something other than vapor pressure, I don't want to talk about that anymore. If you need me to explain something, please type a comment. Let's see where we're at. We're down to 3 people yet? No, still got 4. Fantastic. Heat problems. Complete the following temperature conversions. So whenever you're going from Kelvin to Celsius or Celsius to Kelvin, the easiest thing to do is to look on your reference table, and it actually tells you standard temperature. Standard temperature is where 0 degrees Celsius is equal to 273 Kelvin. And that one thing right there helps you determine what you need to do. If you're going from Celsius to Kelvin, you're going to add 273. If you're going from Kelvin back to Celsius, you're going to subtract 273. Super simple. So at 473, I'm going from Kelvin to Celsius. 473 minus 273 gives me 200 degrees Celsius. All right, next one. 100 Kelvin to Celsius, still Kelvin to Celsius. So I'm going to subtract 273. So I'm going to get negative 173 degrees Celsius. Now this one, I'm going from Celsius to Kelvin. So I'm going to add 273. So this one becomes 373 Kelvin. There you go. That's how you do it. And honestly, that little diagram right there, I've been doing these calculations for a long time, and I still write that sometimes just to make sure I know what I'm doing. All right, number 2. This is a 5-step problem. It's not a very hard one, but we can do it. It says a 15.75 gram piece of iron absorbs 1,086.75 joules, that's important, of heat energy, and its temperature changes from 25 degrees Celsius to 175 degrees Celsius. Calculate the specific heat capacity of iron. So we're looking for specific heat. There's our target. So step number 1, as I've taught you guys, is you write what you know. Well, we know mass, 15.75 grams. We know Q is 1,086.75 joules. Let me zoom in, y'all. It's really small. There we go. And we also know temperature. Now, remember, when we're using this equation, it's actually going to give us delta T. That's what we want. Now, remember, delta T is final minus initial. So my final, notice it says the word 2 here. It's going from 25 to 175. So the final temperature is going to be 175. At the end of the problem, it's going to be 175. So it's going to be 175 degrees Celsius minus 25 degrees Celsius equals delta T of 150 degrees Celsius. Now, in case you're asking and saying, well, Mr. Aaron, do we need to convert that to Kelvin? No, you don't need to here. In fact, if you look on your equation sheet, whenever they're talking about specific heat, degrees Celsius is what they're using. The only time you need to convert from Celsius to Kelvin is when you're doing gases. If you're doing gases, whether it's combined gas law, Dalton's law, Boyle's law, Gay-Lussac's law, any of those, then you convert to Kelvin. All right, but here we don't have to. And then next step, what are we looking for? Well, we're looking for CP. That's specific heat. So there you go. Step 1, check. Step 2, check. Step 3, what equation do we want to use? Well, it's pretty easy. Q equals M times Cp times delta T. That is the one that we want. Now, if we're looking for specific heat, just like we did on our quiz earlier, we need to rearrange this to solve for Cp. And so instead of multiplying by M, I'm going to divide by M. Instead of multiplying by delta T, I'm going to divide by delta T. And when I do that, it cancels those. Whatever you do to one side, do to the other. And then I end up getting that. So let me rewrite this mess. So Q is now over M, and it's over delta T, and this is equal to Cp. All right, as demonstrated, that's what we're looking for. Tell you what, you guys will probably like it better if I write it this way. Cp equals. All right, you'll probably appreciate that. So there we go. Step number 4, plug all this junk in. So Cp is what I'm looking for, so I'm going to leave that as it is. Q, I can see over here on my list. Q is 1086.75 joules. All right, you've got to put units. Okay, you don't want to use watermelons. Make sure you use joules. And this is going to be divided by M, which is 15.75 grams, times delta T, which is 150 degrees Celsius. Wow, I did not give y'all a lot of room to write for this problem. I apologize. So step number 5, what the heck is Cp equal to? Well, I'll get my calculator. I'll tell you in a second. In my calculator, I'm typing 1086.75, and I'm dividing by 15.75. Enter, I get 69. But I've also got to divide by 150. Hit enter, I get 0.46. Well, 0.46 what? Well, look at the units above. If you look at the units above, you can see we had joules divided by grams divided by degrees Celsius. And so there are our units. And I'm going to box this because I always box my final answer, and you should too. Number 3, how much energy must be absorbed by, how much energy, so there we go, that's probably what I'm looking for, must be absorbed by 20.0 grams of water, ooh, that's important, water, to increase its temperature from 283 degrees Celsius to 303.0 degrees Celsius. The fact that they said water here instead of ice, instead of steam, tells me I'm probably dealing with liquid water. So that's going to be pretty important here in a second. So let's write out the stuff that gives us. And I actually have room to write this time, so it'll actually be really nice. So first things first, here's Ti, here's Tf. So I'm going to go ahead and do my delta T calculation. Remember, it's final minus initial. So I'm going to do 303.0 degrees Celsius minus 283 degrees Celsius. And I get delta T is equal to something, 30, 20. I think it's 20, yeah. 20 degrees Celsius. So there you go. There's delta T. We also know the mass. It tells us it's 20 grams of water. And there's one other piece of information that they give us that is on the reference table. Because on the reference table, it says specific heat of water is 4.18 joules per gram degrees Celsius for liquid water. It says it. It's right here on the sheet. All right. So for liquid water, there you go. 4.18 joules per gram degrees Celsius. Yay, we did it. Now, step number 2. What are we looking for? Well, it tells us how much energy. So we're looking for Q. And I know you guys hate that. I know that you hate that it says Q instead of E, but it's because it stands for quantity of heat energy. So we're looking for Q. Well, luckily for us, there's an equation that has all of these things, and it's the exact same one that we just did. Okay, so there's the equation. I'm going to plug everything in. Q is what I'm looking for, so I'm not going to rewrite it. M is going to become 20.0 grams. Cp is going to be 4.18 joules per gram degrees Celsius. And delta T, we found 20 degrees Celsius. So I'll just multiply everything together. 20 times 20 is 400 times 4.18 is 1672. 1672 what? Mr. Naren, is probably what you're thinking. Well, let's look. There's grams, there's grams, there's Celsius, there's Celsius. All that I'm left with, joules. And that makes sense because we are dealing with energy, quantity of energy, and energy is always measured in joules. And no, it's not this kind, it's this kind. All right, so there you go. I think I spelled that right. I don't know, I don't vape. It's dumb. Number 4, how much heat energy, ooh, no wonder my mouse is so sensitive. How much heat energy is required to melt 360 grams of solid water, also known as ice? So, how much heat energy, we're looking for Q again, is required to melt 360 grams of solid water? That is a piece of information that they're giving us here. So, once again, we'll say, all right, well, we know we got mass equals 360 grams. If you're confused, you could start by saying, well, how much, we're looking for Q. What is Q? Well, what do I have that has Q and M in it? So if you get caught, just look and say, what has Q and M in it? Well, we got MC delta T, but it doesn't say anything about temperature, so I can't use that one. Oh, here's one. Here's MHV. Okay, here's MHV. Now the V, HV stands for vaporization. But I'm not vaporizing anything here, I'm melting. So the very next one, and again, I'm literally just looking at the equation sheet. The very next one says Q equals MHF. I'm going to go ahead and write it. And if you're saying, well, Mr. Aaron, I'm not fusing anything. Yes, you are, because I told you that melting and fusion are really the same thing. So if they say melting, what they really mean is fusion. And when they say fusion, what they really mean is melting. So this is the equation that we need. And before you say, oh, well, Mr. Aaron, we don't have HF. Yes, you do. Heat of fusion, I'll look back on the front page of my reference table. They separate it just to annoy you. It says heat of fusion of water is 334 joules per gram. So there you go, straight from the equation sheet. You just got to know where to find it. Okay, now that we got that, I guess we better plug in some numbers. Q is what we're looking for. M is 360 grams. And HF is 334 joules per gram. So Q equals a number. Hold on. 120, 240 watermelons. No, I'm just kidding. That would be ridiculous. If you look, you can see that grams canceled. See, we had grams there, we had grams there, and we were left with joules. So this is going to be joules. Okay. All right, guys. Right now, because I'm kind of curious who's watching. We got 5 people. Holy cow. Tell me, how are you feeling about these problems that I've done so far, 1 to 5? 1 being this is really hard, 5, I'm getting it. Okay, 1 to 5. 1, I'm not very comfortable. 5, this is the easiest thing I've ever done. And if you're at a 1 or a 2, please type me how I can help you. I'm going to give you a second to get caught up. I'm going to do number 5, probably silently, but go ahead and answer that real quick. So yeah, I'm curious. How are you guys feeling about this? The reason I'm not going over number 5 the same way is because it's basically the same as the previous problem. The only difference is this word right here, vaporize. If they're talking about vaporize, good, we got 5. If they're talking about vaporize, they're dealing with the MHV equation, and that's the only difference. So I'm going to use HV instead of HF. Wow, 4.032. That is so specific. Thank you. We'll have to increase that by 0.968 and we'll be doing good. All right, so HV is another thing they gave me. It's 2,260 joules per gram. Anybody else? Okay. Well, anyway, I'm just wrapping this problem up. It's basically the exact same. It's just that we're using HV now instead of HF. All right. There you go, number 6. Because this one is a little bit tricky. All right, a 4. I can handle a 4. When 80 grams of a certain metal at 90 degrees Celsius was mixed with 100 grams of water at 30 degrees Celsius, the final equilibrium temperature of the mixture was 36 degrees Celsius. What is the specific heat of the metal? A calorimeter is something that we didn't really, like, if it had been ideal circumstances, we would have done a whole lab with it and everything. But we don't really have time for that, or the ability. So let me show you what it looks like. So a calorimeter is you can think about it like a styrofoam cup or a double styrofoam cup. This one will work. And so you have 2 styrofoam cups mixed in. You have some water in the inside. You have a thermometer, and then you have a little stirrer. But what's important is you know what the temperature of the water is before the experiment begins. So if you're like, oh, well, the initial temperature is 22 degrees Celsius, that's fine. But then what you take is usually a hot cube of something. Maybe it's brass, maybe it's iron, maybe it's nickel. And you take that hot cube, and you know what the initial temperature is. You'll know what it is. And you say, oh, well, it's initially 50 degrees Celsius. When you drop it in the water, the cube of metal is going to keep getting cooler, and the water is going to keep getting warmer until what happens? They become the same. And so by doing that, that is how they get all those specific heat numbers, is they find out, okay, well, we know what the specific heat of water is. So what is the specific heat of the metal? And so they use these coffee cup calorimeters to do that. So now that we got that out of the way, that's really all we're doing here. But it's just going to be this equation. And we're just going to use this equation because we have all that information. We're going to be looking for CP, so we'll have to rearrange it in a second. But here, let me prove it to you. 80 grams. It was at 90 degrees Celsius. Okay. And then later, it was 36 degrees Celsius. What is the specific heat of the metal? So here's what I did here, because this is kind of a confusing problem, because a lot of you guys are going to be like, oh, Mr. Aaron, don't we need to know? It says 100 grams, so how do I know to use 100 or 80? Well, think. It says, what is the specific heat of the metal? So if we're looking for the metal, you just have to make sure you pick all of the numbers that correspond to the metals. All right, so 80 grams of a metal, 90 degrees, okay, is what the initial temperature was. Final temperature of both was 36. So we don't really care so much about water. We are only interested in the metal. And so that's why I'm highlighting only that. And so what we're looking for, here I'll do it in blue, what is the specific heat of the metal? So there you go. There's our target. Let me write some junk down. First things first, we can go ahead and do our delta T. We know it's T final minus T initial. T final, it even says right here, final temperature was 36. So I'm going to do final, 36 degrees Celsius minus initial, 90 degrees Celsius. Okay, 90 degrees Celsius. Hold up. Ah, I do need that information. Dang, I forgot this one's slightly weird. Big step back. I'm still going to use that delta T. I'll get back there in a second. We do need that stuff for water because the thing is they didn't give us a Q. But as we learned earlier, in fact, let's scroll back and remind ourselves. It says law of conservation of energy. It is that energy is never lost or gained. It's only changed in form. It goes from one type to another. So what we're looking at in this problem here is that Q, even though we don't really know what it is, think about it this way. The Q that the water gains, because isn't the water warming up? You put that hot piece of metal in there, water's warming up. The Q that the water gains is equal to the Q that the metal lost. The metal's getting colder and colder and colder the whole time. So really what we're doing here, and I'll say number 6 is probably the hardest one on the worksheet. Let me double check myself, but I'm pretty sure it is. Yeah, it's still pretty hard. Is you have to understand that, oh, well, Q of water, grams of water, it was at 30. Its final temperature was 36. So we can say, oh, well, then Q for water gains, why don't I just say MCP delta T of the water? And all this is going to correspond to water. And for the metal, Okay, maybe we do the same thing for metal. MCP delta T for the metal. And again, we'll be using all of this to find CP of the metal. All right, so clean slate. Let me clean this up a little bit. Let me clean it up just a little bit. So we are looking for specific heat of the metal. That hasn't changed. In terms of the metal, we know it's 80 grams. We know that it was at 90 degrees Celsius. We know the final temperature was 36 degrees Celsius. Okay. And in terms of water, we know that it was at 30 degrees Celsius. It's 100 grams of water, and we know its final temperature is 36. But another thing that we know about water, just because we always do, is that CP of water is going to be equal to, and we're done with liquid water. So liquid water is 4.18. Okay, and I know that because it's on the equation sheet. So we know 4.18 joules per gram degrees Celsius. So here's what I'm going to do. I'm going to break this problem into a couple different lists. We know that we're looking for CP of the metal. Okay, so here's my metal list over on the right side. I'll have my water list over on the left side. So we still need to find delta T. Delta T for the water, final minus initial. Well, final temperature is 36. Initial temperature of the water was 30 degrees Celsius, right? We can see that in the problem. It was at 30. And so I end up getting delta T equals 6 degrees Celsius. So there you go. There's delta T. Another thing we know about water is we know the mass was 100 grams. So there you go. There's all the information that we have about water. Now, for the metal, we know the delta T for it as well. Final temperature is still 36. Initial temperature is 90. Okay, and so we can do 36 minus 90, and we get negative 54. So there you go. There's my delta T. We also know the mass. Mass is 80 grams. So as you can see, I have two lists. I know I'm looking for CP. I'm going to now put everything in one equation, represented with blue, I guess. So here's the thing. Q of metal, you can think about it this way, would be equal to the Q of water, except it's going to be negative because the metal is getting colder, right? It loses its heat energy and gives it to the water. So it'd be a negative Q of metal, positive Q of water. But let's think, what's Q equal to? Well, it's equal to MCP delta T. Q of water, same thing, MCP delta T. All right? Now, this is where it gets kind of interesting because we have to be careful to keep our water values separate, okay, or know that, yeah, that's M, but that's M for water. Yeah, that's CP, but that's CP for water. So you have to know that that's that side. And then on the left side, this is all the stuff that has to do with metal. So we've just got to be kind of careful when we're plugging numbers in. Okay, we can solve for it algebraically. Basically, what we end up getting, because I'm gonna spoil it for you, we end up getting CP is equal to MCP delta T over M delta T. And the way that I tell the difference between the two, this down here has to do with the metal. This stuff on top had to do with the water. So I'm still keeping them separate, but I'm solving for CP that way. All right, let's plug some junk in. All right, I'm going to scroll over just a little bit. Start plugging in some numbers. Whoa, that's too far. Okay, here we go. CP, that's what we're looking for. All right, M, this is mass of water, was 100 grams. CP, 4.18 joules per gram degree Celsius. And delta T of water was a positive 6 degrees Celsius. Now, all this is over the mass of the metal, which was, 80 grams, times the delta T of the metal, negative 54 degrees Celsius. Okay, and now math happens. Give me a second, and I'll tell you what CP I got. All right, 100 times 4.18 times 6. I'm going to divide this by 80, and I'm going to divide that by negative 54, which honestly, we don't have. The negative is going to end up giving you a negative specific heat value. I forgot that really there should have been a negative right here. You guys see this really obnoxious negative symbol I'm writing over there? So really I should have accounted for that algebraically. I'm just going to write it as a positive number. And the reason I'm going to is because all the CP values are positive values. You can look on your equation sheet and see that all CP values are going to be positive. It wouldn't make sense if it were negative. So that's what I get. So that is a heck of a problem. In fact, we can actually find out that this is probably titanium. So not that the problem asks for that, but it certainly seems like it's probably titanium. You can look at the reference table and see that's the specific heat that we got. Cool. Well, that problem was fun. All right, guys, that one's really, really hard. Don't sweat that one too much. I know that was difficult for you guys. I know it was. Okay, let's take a look at these next one. These are a little easier. Okay, endo versus exo. So remember, I've said this before, but in case you've forgotten, when you think about exo, you need to think about energy exits. And when you think about endo, you need to think about it as energy in. Okay, energy exits is exo, energy in is endo. So try and keep that in your mind. All right, blank, a reaction that results in energy being absorbed by the reaction. If it's absorbing it, energy's coming in, that's going to be endo. Done. Next one, a reaction that results in energy being released. If energy is being released, that means energy is exiting. This means it's going to be exo. There you go. Next one, a reaction that feels warm to the touch. Now, if it feels warm, okay, if it feels warm, then that means it's releasing energy. I'm going to say it again. If it feels warm, the reason it feels warm is your hand is taking energy from it, the object. So like, I don't know, hot hands is a good example. I had to use hot hands Sunday morning because it was like 30-something degrees outside. But hot hands, they feel warm because they're releasing all that heat and your hand is absorbing it. So energy is exiting the reaction, so that's still going to be exo. Next one, reaction that feels cool to the touch, like an instant ice pack or something like that, a cold pack. That feels cool to the touch because it's endo. It is taking energy from your hand into it. So the reason you feel cold is because heat was lost by your hand and gained by the substance. So this is going to be endo. There you go. And then we got two diagrams here. Basically what you need to look at is, look, here's reactants, here's products. You can see that energy came in throughout the reaction because it has more energy at the end than it did at the beginning. And so energy in, this is endo. I'm going to go out on a limb and say the other one's exo. Let me show you why. Look how much energy the reactants have, and then look at how much energy the products have. This is because energy exited. Where did it go? I don't know. It went somewhere else. It went into something else. And so that's exo. All right. We're home stretch-ish. All right, here we go. What does STP stand for? STP stands for standard temperature and pressure. There you go. That's what STP stands for. Standard temperature is going to be either 0 degrees Celsius or 273 Kelvin, like I told you guys earlier. Standard pressure is 1 atmosphere, or you could say 101.3 kilopascals, or you could say 760 torr, blah, 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 blah. But that's what it is. Scoot this over just a touch. There we go. All right, number 2. How much volume does 1 mole of gas occupy at standard temperature and pressure? Let's look at the reference table. Reference table says volume of 1 mole of any gas at STP, 22.4. There you go. Number 3, what does it mean for a gas to be considered ideal? If you look in your notes, there's lots of things I told you about this. Here's just a few pieces that make it ideal. You have to assume gas molecules are very far apart. My voice is starting to give out on me. Assume gas molecules are very far apart. You have to assume near or at STP. Okay. And you also have to assume intermolecular forces. You guys remember those? Dipole, dipole, polar, London dispersion. You have to assume intermolecular forces don't do anything. And most of that is because they're very far apart. So there you go. That's good enough. That's what means it's ideal. Because the thing is, if you get at really high temperatures or really, really, really low temperatures, gases don't behave ideally. And also, if the molecules are really, really close together, IMFs do something. And that starts to make it so they don't behave very much like gases and they start to behave more liquidy. And that's not what we like. So these are the things that we're assuming to make it ideal. All right, let's fill in some blanks. Okay, blank can be used to determine, blank can be used to explain each of the experimentally determined blank. Wow. Gas laws. I haven't done this in a while. I think this is kinetic molecular theory. Can be used to explain each of the experimentally determined gas laws. The blank of a gas, that's probably pressure, results from collisions between gas particles in the walls of a container. When a system is in chemical equilibrium, the physical state of the system does not change. Physical equilibrium. Oop. Sorry, got those a little confused. Sorry, this is physical equilibrium. And then this is going to be chemical equilibrium. There you go. Is the state in which the concentrations, yeah, that's it, of reactants and products do not change. All right, there you go. Gas problems. Let's get to it. So gas problems, I'm going to do them not super fast, but I'm not going to do them super slow either because honestly, these are just 5-step problems. Oh no. Phone call. I'll be right back. You guys get called up. Guys, I do apologize. That was house stuff, so excuse me. All right, let's get back to work, shall we? And I do apologize. That's so unprofessional. I hate to do it. Gas problems. Let's go. Number one, as we're wrapping this up, 1 liter of a gas at STP. That just told us a lot of information. Okay, is compressed to 473 milliliters. What is the new pressure of the gas? All right, so 1 liter of a gas at STP is compressed. What is the new pressure? All right. So the important thing here is they're giving us two different volumes. They're telling us that the initial volume, or volume one, sorry, I like to say initial and final, and my wife likes to say 1 and 2 because that's what they say on the reference table. So let's just say 1 and 2. So V1 is going to be 1.0 liter. V2, I don't really like how it's written as 473. I'm going to go ahead and convert it. That's the same thing as 0.473 liters. So now everything's the same. And if it were at standard pressure, that means P1 was probably 1 ATM. So what we're really looking for here is P2. We're really looking for P2. So there you go. There's steps 1 and 2. Excuse me. Not used to talking so much. I did an AP video and now I'm doing this one. What I recommend to you guys, and I know I've said it before, is always start by writing the ideal gas law, sorry, combined gas law. And then you basically just get rid of what you're not dealing with. Does it say anything about temperature? No, it doesn't. So we have to assume that temperature stays constant. So what I'm going to do is I'm just going to make temperature disappear. And so if temperature goes away, we have P1V1 equals P2V2. All right. And so if I'm looking for P2, well, let me do it in red. If I divide by V2, that cancels it over here, puts it over there that side, and then now we have P2 by itself. So rewriting all that then, and I know the algebra is what you guys have been struggling with. P2 equals P1V1 over V2. I am using the exact same process. If you need to get rid of something, do the opposite. Whatever you do to one side, you do the other side. So let's plug in some numbers. P1 is 1 ATM. V1 is going to be 1.0 liter. And this is all going to be over V2, which is 0.473 liters. And there you go. Let's put some stuff in the calculator. I'm not going to do 1 times 1 because that would be ridiculous. But I'm going to do 1 divided by 0.473. And I get 2.1. And it's at this point that you guys know what I would say. I would say 2.1 what? Watermelons? Probably not. If we look at the equation, we can see that we have liters. Liters cancels. We are left with ATM. So this is going to go ahead and be ATM. There you go. And I'm trying to squeeze it in on the screen. Moving on, number 2. How hot will a 2.3 liter balloon have to get? Okay, so there's 2.3 liters. That's important. Have to get to expand to a volume of 400 liters. I am 90% sure this is a typo because I remember doing this last semester and it was a stupid answer. I think it's supposed to be 40.0 liters, but 400 liters. Why not? That's going to be crazy. The initial temperature of the balloon was 25 degrees Celsius. Now, remember, when you are dealing with gas law problems, you have to do Kelvin. You can't use Celsius. You got to use Kelvin. All right, so let's write out some stuff. Initial volume was 2.3 liters. Final volume is 400 liters, which again, that's ridiculous. That's 200 2-liter bottles from one. You start with one 2-liter bottle. How do you make that the size of 200 of them? It's just crazy. And then we also need, let's see, how hot would be the initial temperature? So T1 is 25, but we don't want that. We want Kelvin. So I'm going to do 25 plus 273. Not sure why I typed that in my calculator. I get 298 Kelvin. And that's the number that we want to use. Okay, now the internet is all going badly. But anyway, we got to keep pushing. So basically T1 is going to be 298 Kelvin whenever it eventually loads on the screen. There it is. And we are looking for T2. All right, so there we go. We're looking for T2. It's going to be really hot. Spoilers. So once again, if I look at it in terms of ideal gas law, combined gas law, I'm going to write out the full gas law. But what is it that we're not considering this time? Pressure. Pressure is the thing that we're suddenly not interested in. So if I make pressure disappear, I have V1 over T1 equals V2 over T2. All right, and so what are we looking for? We're looking for T2. This is the bad algebra one that everyone hates. So tell you what, I'm just going to skip to the end and tell you T2 is equal to, give me a second. Yeah, that's it. I think. Be right back. Yeah, that's it. Okay, so anyway, there you go. I did the algebra for you. That's what we end up getting. So let me clean this up a little bit so you guys can see what we're talking about. There we go. Alrighty, so we've done that. Now we got to plug some junk in. T2. If you guys really want me to explain the algebra there again, I can. I know that number 2 is like the weirdest algebra we have to do because you have 2 fractions. If you really want me to explain it, you can type it, but otherwise we're just going to keep on rolling. So T1 is 298 Kelvin. You will not use degrees Celsius when you're doing gas stuff. V2 is 400 liters. And this is all going to be over V1, which is 2.3 liters. Okay, so there we go. There we go. Load, dang it. All right, there it goes. So 298 times 400, and I'm going to divide that by 2.3 liters, and we get 51,826 Kelvin, which is hotter than like, I don't know, it's like 10 times or 5 times the temperature of the surface on the sun. So, yeah, that's why I think this problem's kind of bogus. But it was fun. That's really hot. All right. Number 3, given 4 moles of a gas. I'm going to go ahead and start by writing that out. And again, nobody's saying anything about the algebra. Have I lost all my viewers because I had to take that intermission? Oh no, we got 4 people. That's pretty good lately. Given 4 moles of a gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temp of a gas? Whenever you guys see the word moles and they're talking about gas, you know you're dealing with ideal gas law. So 4 moles of a gas, 5.6 atmospheres, 12 liters, what is the temperature? So that 5.6 atmospheres is going to be important in a second, but let's go ahead and get our list made up. N equals 4 moles. Okay. Pressure is going to be 5.6 atm. Okay. And the volume is 12 liters. What is the temperature? Okay, so as you can see, we got P, V, N, and T. But Mr. Nairn, I thought ideal gas law looked like this. Yes, it does. So we need to get R. Now, as I've told you 1,000 times, or what feels like 1,000 times because I've taught it a few times, if I look at gas constant, I have 3 different ones. But remember, the units of pressure in this class, the units of pressure are going to determine what we use. So if I have atmospheres, I need to use the R constant for atmospheres. So R for me, for this problem, is going to be 0.0821 liters times atmospheres, see, that's why it matters, over moles times Kelvin. So there you go. There's our R value. All right, so what are we looking for in this problem? We're looking for temperature. So I just need to rearrange my equation to solve for temperature. Just like that. Okay, and so T is equal to PV over NR. And so now I got to plug in some numbers. P is 5.6 atm. V is going to be 12 liters. And this is all over 4 moles times 0.0821 and all this junk. So there you go. Looking for T. Math. Be right back. So I have 5.6 times 12 divided by, hit enter. So I did 5.6 times 12, enter, divided by 4, enter, divided by 0.0821, enter, and I got 204.6 if you care, Kelvin. And how do I know it's Kelvin? Because if you look back at the units, look at what cancels. Atmospheres, atmospheres, liters, liters, moles, moles. And what are we left with? K for Kelvin. Okay, there you go. Number 4. A mixture of neon and argon gases exerts a total pressure of 2.39 atmospheres. The partial pressure of neon alone is 1.34 atmospheres. What is the partial pressure of argon? Whenever they start talking about partial pressure, you know you're dealing with Dalton's law. If you've forgotten, Dalton's law looks like this. And you just do it for as many pressures as you need. In this problem, we're only dealing with 2 gases. So we only need 2 pressures. All right, so let's write out so you guys can see what I'm talking about. We know total pressure is 2.39 atm. We know that. We also know partial pressure of neon is 1.84 atmospheres. So what are we looking for? We're looking for the partial pressure of argon. So there you go. That's what we're looking for. So this equation then, for this one, instead of using 1 and 2, which if you want to use 1 and 2, you go right ahead. I've just changed the subscripts to reflect what they're actually talking about in this problem. But that's all we're really doing here. That's all we're really doing. Now, we're solving for partial pressure of argon. So we need to rearrange for it. Remember, to get rid of something, you have to do the opposite. So if I want argon by itself, I have to get rid of that neon. So instead of adding, I'm just going to subtract. And whatever I do to one side, I have to do the same to the other side. So what do I end up getting? I get PAR equals P total minus P neon. There you go. Excuse me. All right, let's plug in some numbers. P argon is equal to 2.39 atm minus 1.84. Wow, that was great, Aaron. That was a good 4 atm. And so P argon equals something. 2.39 minus 1.84 equals 0.55. 0.55 what? And let's go ahead and make it atmospheres. We are dealing with pressure. Atmospheres is what was used in the rest of the problem. It's just going to end up being atmospheres. All right, the last one, the hardest problem. That does seem like a lot for simple subtraction tests. It's just that if you don't do all the steps, I've seen a lot of students that just start adding the numbers together. I'm serious. I'm not trying to roast physical science students here or anything, but like I teach something similar in physical science, and when I do this in physical, if students see 2 numbers, they're either going to add them both together, multiply them all together, divide them, like they'll just do a random, operation. When you do it this way, that helps you know exactly what you should be subtracting, and it lets you know what are you subtracting from what. So yeah, it seems like a lot for subtraction. I hear you, but I have my reasons. Number 5. This one's going to be great. Before my voice gives out. A 6-liter sample at 25 degrees Celsius and 2 atmospheres of pressure contains 0.5 moles of a gas. If an additional 0.25 moles of gas at the same pressure and temperature are added, what is the final total volume of the gas? What in the world am I doing here? Okay, I'm looking for final total volume. The first sentence is a waste of time. So this is kind of a trap because you've got to think, okay, what am I actually looking for here? Well, I know I'm looking for volume. I know I'm looking for this total volume. But another thing we know is we're not going to use 0.5 moles or 0.25 moles. Because in our ideal gas law, because remember what I told you, if they ever are talking about gases and they say mole, it's ideal gas law. So in fact, let's go ahead and write that out. I just said we're looking for volume. Let's go ahead and solve for volume. So here's what we got then. The reason this question is a trap is it makes you feel like, oh, well, do I have to do ideal gas law twice because they gave me all these numbers? No, because if you look in the first sentence, they gave you volume, temperature, pressure, number of moles. The only thing you're missing is R, which is the gas constant. So if it's a gas constant, that's not going to change. So there would be literally no purpose in just plugging all those numbers in the first sentence into one equation. That would give you nothing except the gas constant that you already know because it's written on this piece of paper. So in the second sentence, that's when it starts to make a little more sense. If an additional 0.25 moles of a gas, pause. How many total moles am I dealing with then? Because I had 0.5 in the first part. I have 0.25 moles in the second part. So I'm dealing with 0.75 moles total of this random gas that I have. Okay, so there we go. I've already dealt with moles. Check. R, do I know it? Yeah, but I better write down pressure first. It says right here, it's at the same pressure as it was in the previous problem. So pressure, still going to be 2.00 atm. Temperature, still going to be the same temperature, but be careful. Remember, we know it's going to be 25 degrees Celsius, but we don't want Celsius. We want Kelvin. So add 273 to that thing, and you get 298 Kelvin. So look at what we got. We got pressure. Okay, we have T. I have to sneeze. Excuse me. And we have R because it's a constant. Now, which R are we going to use? Well, let's see. Look, here's atmospheres right here. And so if we're using atmospheres, we have to use the one that corresponds, with atmospheres. So 0.0821 liters times atmospheres over moles Kelvin. That's the one that I'm looking for. So even though this problem throws a lot of numbers at you, it's really not that much harder than any of the other ones. That's the difference between a math class and a science class. You have to be able to use logic to figure out, okay, what are they really talking about? What are they really looking for? So now that we know everything except what we're looking for, which is volume, let's go ahead and plug everything in and see what we get. Scroll a little bit. That's too far. All right. Let's put everything in. Volume's what I'm looking for. I'm just going to rewrite it. Number of moles is 0.75 moles. R is going to be 0.0821 liters times atmospheres over moles Kelvin. Okay. T is going to be 298 Kelvin. And all of this is going to be over the pressure, which is 2.00 atmospheres. Okay, there you go, 2.00 atmospheres. So I'm going to plug all this stuff into a calculator, and you can do all this in one step. It's just you've got to be really careful about your parentheses. I'm just going to break it up into smaller steps to make it easier on y'all. So I'm doing 0.75 times 0.0821, enter, times 298, enter, divided by 2, enter. And I get 9.17. 9.17 what? Well, we are dealing with volume, and usually when we talk about volume, we use liters, but let's double check. Look back at the last step. Moles cancels with moles. Kelvin cancels with Kelvin. Atmospheres, atmospheres, and what do you know? We're left with liters, so we get that right there. Okay, guys, hope that was helpful for you. Take a second. If you do have any other questions for me before my voice gives out after an hour and a half of this, please let me know. Please let me know. My voice is about done. So if you have questions, ask me. That's good. I'll check this text message that seems, I don't know, sort of seems important. Did you get the text message? Anybody? Anybody have any questions before I wrap this up? Excuse me. Give you 30 more seconds. Give you 30 more seconds. Enthalpy is, it's not really something you need to focus on too much. Do you need help with vocab for enthalpy, or you just want me to explain what enthalpy is in a couple of sentences? Because enthalpy is just like heat energy. Earlier I was talking about hot hands. Hot hands do not last forever. You get your hot hands, you take them out of the package, you shake them a little bit, and they are going to release a certain amount of heat until the reaction is finished. Until you completely run out of reactants and everything becomes products, it's going to go from reactants to products until it's completed. Enthalpy is the total amount of heat energy that it released while it was active. So enthalpy is just a quantity of energy present in a reaction. There you go. So for vocab, what do you want with sentence? You want a picture? Because if it were a picture, I would draw something probably like this. So if I were doing enthalpy, I'm going to write it right here. I would draw a picture of hot hands, like so. And I would draw waves coming off. It looks like a bar of soap, but anyway, hot hands. And I would say something like, I don't know, 203 kilojoules is released, and that's enthalpy. That's all there is to it. If I were doing a sentence, I gotta remind myself what the definition is, because I don't want to just rewrite. I don't want to just re-say the definition. I know what the definition is. I want to know what my definition is, so I don't just put it in a sentence. Let's see if this opens. Should be nice. Scanning. Heat content of a system at constant pressure. Yeah, I probably won't say it like that. Heat content of a system at constant pressure. If I were writing a sentence, yeah, it's easier to just do an example. There you go. That's what I'd probably say, something like that. I said the enthalpy of hot hands is the total amount of energy it releases until the reactants are used up. No, that's okay. It's just the thing is when you teach day after day after day and you talk constantly, your voice gets used to it. But because I've been relatively quiet lately, this is hard for me. But no, if you got questions, please ask them. That's what this is for. That's what this is for. So if you have questions, ask me. It is my job. There's only 3 people here, so it's basically just the 3 of you and me, and I'll answer any questions you got. Besides, I got water. I'll give y'all 30 seconds. If you don't say anything, I'm going to end it. Calorimetry. sentence or picture? You gotta specify for me. If I'm drawing a picture, I just draw a coffee cup calorimeter like I showed y'all earlier in the video. I showed you that coffee cup calorimeter. If you need a sentence, make sure I don't say just my definition again. Here we go. Yeah, this is an easy one to do a sentence for. Let's see here. There you go. And if I were drawing a picture, like I said, I would draw a coffee cup calorimeter, something like this. Be like, all right, we got our coffee cup. Wow, that looks great. It's got some water on the inside. I'll draw that. I would draw my test subject. Okay, I'm going to just make it a little cube of titanium. We also want to draw a thermometer. We need to put a lid on it. Okay. And that'd probably be about it for me. I think I put the thermometer in the wrong way, so just pretend like I didn't. Or, ooh, can I do this? Maybe tense. Can I do that? No, I can't. So yeah, I think I did the thermometer in the wrong way, but yeah, whatever. It's not real. Anything else? All right, guys. I think that's going to do it for me. If you need anything, you can always email me. I'm around. I hope everybody's. Oh shoot! Did I not? Okay, good. I did post desktop screen. Sorry, I thought I was just doing my face the whole time, and I'm like, that's not very useful. If you need anything, you know how to find me. Hope everybody has a good one, and I will talk to you soon.